Welcome guys to a new video, and in this video let's talk about the mk1 rotor that is being inspired by SARCnet mk1 rotator. And here we have used AVR controller, Arduino, and an H bridge driver and two geared motor. Those are offside axial uh, geared brushed motors, and the mem sensor right over here. You can see I will give you guys a complete description and the component selection later in this video, and let's just talk about the design. You can see the motor right there poking through, and this PVC pipe is being held right there along the sensor. And here we have two motors and a buzzer for calibration, and this whole system supported over there via some nuts and bolts. And currently it is run by a 12-volt supply. There you can see the supply wire is coming right here, and the USB connection from the AVR coming towards the computer. And here is a small demo program that is being run, and the demo program consists of only azimuth and elevation in incremental order. And if you here the you can see the serial monitor. The values are actually going into the system, and it is incrementally increasing the, you can see the board is not properly connected, so the program is right now there to move this towards incremental values of azimuth and elevation. Right there I have started the program again, and you can see the incremental order going over there. I will provide you the program in the description. There they have a few different programs, menu sets to, you can see few different menu sets over there for say C for calibration, S for save, different kinds of commands that you can then put it in. And you have to select the carriage return and proper baud rate to see the sensor data as well as rotate the system. So here if I abort the test, the rotor gets to its resting position, which is the north, and elevation of 0. So if I say let's do the what are the sensor is seeing, let's say motor control M. If I press the M command, it will show me the current that is the azimuth and that is the elevation, and here are both instructive. So whatever I put in the program, that will show the angle of azimuth and angle of elevation will show over here. That is the targeted value, and here are last two digits are offset values. That is the output of the program, which is these two columns, these two you can see, and these two rows, and that last two row will show the error of the program. So let's say if I put a command of let's say 20 space 20, so the motor right now like this, if I hit enter, it will run towards 2020, and you can see first two digits turned. These are the current value that you can see is changing, and this is the desired value that I have just put in, and here are the continuous factors are calculating how much error are there. So if I abort the program, the system goes back to its resting position, and I will do the demo, and the rotator will slowly start rotating, and it will complete the whole cycle. It will go at the north direction and going all above up towards the southward direction. So so once the setup that you have already completed, after that your device must have to have two softwares. One is gpredict to track the satellite in real time, and another program is called hamlib. That hamlib program that you can see, that is a library that helps your computer to actually talk to your rotator. So this rotator right here, the program that you have just that we have just installed into our rotator, our avr, that talks to a protocol that is called the EasyCom2 protocol. So you have to have this EasyCom2 protocol onto your system, so that the proper talking between the device, our computer, to the rotator is properly achieved. So that will do that process is being done by the hamlib. So you have to have hamlib installed on your computer. In here you can see hamlib library. You just have to go to the github, and you have to download your probable version, and after installing you have to create path towards the main two file that you are going to need is rigctl.exe, and the last one is rotcl, that before last one. So these two things you need to have on your computer, otherwise the program will not work. After you have installed those things and create a pathway towards your system. So you have to have a pathway to system, because we are going to control everything by terminal. So after terminal program only you can achieve proper control over your system. So you have to have those two things working synchronously, so that you can coordinately track the satellite. So for this video I am going to keep the information up till now, because after this things will go another separate way and a bit complicated. But just to give you an brief demo, what we have done is, we have this program that you can rotate a 6. You can go over to their SharkNet website and you can download and calibrate everything. And I should have to point you something. Before after programming, all you need to have, this whole system is being calibration is your main challenge. So when you are calibrating your sensor data, by default, when the program that the website offers, there, if you get go close, and if you can see constant ISMA alpha, this alpha value, that is the sensor filter value. So whatever you do, you have to put this sensor value somewhat near 300 0.330 or something near above, because if you put this below, as the website intended 0.05, the sensor will respond much slowly, and the calibration process might might get affected. So you have to have proper this alpha value you have to have properly change according to your system. And also you have to mess with the gain, that is the motor gain, azimuth and elevation. In my case I have set my gain to 5 and 10. You have to fidget with these values somewhat to get your desired, otherwise the system might get oscillations. Sometime the damping is greater so that it goes unstable. So you have to tinker with some of the value like this azimuth and elevation gains and the alpha values, the ISMA alpha values. The for the sensor that you can see it has a comment that tells the decrease to slow response time and ease calibration process. So you have to have a proper in your system you have to properly define these values. And after calibration I am quite sure your module will not uh, be failed, because there is nothing to fail unless your motor and everything will work, because of the closed loop function is so much. So I will show you some of the design problems that I have electrically and mechanically that might get your system to oscillate. In the system that you can see I have wired everything kind of messy, but the key feature that you have to understand is all the grounds of the system must be star connected, so that the minimum noise of the system can be achieved. Here I have used a shielded you can see if I point towards the sensor, over the sensor area I have used shielded wire. If I can focus the camera, you can see there is the shield, that is the USB cable that I have cut and that I have connected, and the ground is properly connected to the shield. That goes over and comes over here. That is the metal area is actually ground, and that ground is also connected via the chassis of the system, that I have this yellow wire connected to the ground, as well as system ground is also negative part is also being connected to the ground. And the yellow wire you can see goes over towards the connection, that is the edge bridge driver, and the middle part you can see the ground part is also being connected towards the ground of the system. So the whole system is properly grounded. So you have to make sure this thing before connecting, and you also have to, if the voltage drop is getting higher, then you must have to connect a electrolytic capacitor towards your sensor area. And when you have done this, everything should work properly. And if I reset the value, it should go over to the resting position. Make sure the sensor gets the proper voltage across 5 volts across their terminal, and every connection must have proper their connection. And internally it has a 5 volt regulator. You can directly connect that to your input of your AVR, and you can get 5 volts from there. And I have used 2 brushed DC motors that are geared, and that is how the whole system is running. And I will be using an Yagi antenna which is tuned to 137 MHz to rotate the system, and I will use a RTL SDR Vlog V3 dongle to receive the data. The main challenge that you are going to face over after creating your motor, the programming part and the calibration part. And for easier calibration I have actually made a structure that helps me properly calibrate my own system. So by bending some of aluminum wire and drilling everything, so this gyro type of platform can move any direction you want, so that the calibration of the sensor can properly be achieved. And if you don't have this, you can directly use a scale to mount the sensor over to your flat surface and slowly kind of rotate it every 12 dimensions, so that the data, you have to make sure nothing ferromagnetic or magnetic thing comes near the sensor, and you have to rotate every single time. Every time you rotate, the beeping alarm beeps, and when it stops beeping, that means that area is being covered, so you have to put the other way. So the calibration process is the trickiest part of the whole system. After that, you just have to follow the proper footstep to get the program running with your computer, and you have to talk to the gpredict and some other programs, so that the whole system can be controlled automatically. So that is other hassle that you have to take care of, because there are lots of protocols that they have used, and rotator mk1 protocol is somewhat relevant, but I seem to have very less knowledge about this, and so I have to browse some more internet and to get proper easy protocol to run everything from your computer. So that's it for this video right now, and that is a not brief but overall demo of the whole system that is being rotating right now. And because the whole loop situation is something that they are running it some way, so there is no stepper motor. So you can imagine, whenever the sensor gets the data, it tells the AVR to rotate somewhat more, so there is a more scope to get error in the system. But the closed loop system has a lot of different aspects to it, because there is a motor, there is the some fidgetiness, there is the structural stiffness, and there is the mounting error, so you have your sensor might get tilted. So there are lots of kinds of error that might get introduced. There are electrical loss. So instead of doing everything, you can just use two stepper or servo motors to get the proper angle. But in this way, you are directly using the magnetic pole and the gyroscopic location factors. The vector control allows the PID and thus controlling the whole system. So that is fascinating, and that is quite accurate actually in some cases. But once the sensor calibration is done properly, you just need to be set up everything properly. After that, you don't need to there do anything. There is no further tuning required, and the current consumption is also quite less. You can see rotor is currently, if the rotor achieves its resting position, they literally there is very less current that it draws. So 0.02 milliampere or something, it's quite efficient. And another aspect that you have to keep in mind, that don't get close to the MEM sensor. Anything that metal, you have to avoid anything that comes near the MEM sensor. You don't put metal screws over them to tighten. You have to make everything electromagnetically separate. Anything metallic will interfere with the calibrated sensor data, so you have to be more careful around the MEM sensor actually. And the programming part and calibration part, I have already told you, is actually more problematic when you make everything. there are all calibration header files that you can go through, and different calibration protocols, the vector library and everything located there. And there are couple of the debugging commands that you can put over there to get proper informations, such as R for resetting everything, C for calibration, S for save, and everything get you can get current data. If I abort the program, the motor will reach to its resting position. And if I show you the sensor, if I want to show you the sensor data, I can press the B for debug. So if I press B, it will show me the current gyroscopic values, and I can just abort this program. And if I go over to the motor, I have already shown you what is the motor data tells the azimuth and elevation. You can put commands like let's say 90 degree azimuth and 20 degree elevation, and if I press enter, it should move towards the 90 degree, and that is the 90 degree, and that is the 20 degree elevation. So the whole system works properly. So let me know if you have any questions around this project. I will post more videos about this once I complete the whole system setup, so that more people can understand how the dual axis system actually you can make it on your own, because I have found very less videos about dual axis tracker mechanism, especially mk1, because there are lots of fidgety things, and lots of things may go wrong. So that's it for this video, and I will see you guys in the next video.